All right, so today we will continue from where we left yesterday, which was the exporting phase. So in case someone just attended the meeting, you can go to the day 2 folder and you can download the Digital Futures Superblock file because we're going to be continuing from that. And let's get started. So yeah, this one. Okay. So yesterday we talked about how to set up our Wallacei X component, like what are the genes, objectives, data, and phenotype. And then we did our first little optimization experiment. We checked the analytics, selection, and everything. One thing which is a bit sad is after we export our phenotypes, like, we did some analysis and we put them in the exporters and then we export it. But after we close our file, okay, I thought, okay, I was thinking it's gonna disappear, but okay, it disappeared. Okay, so here in the genomes, I think we have every genome here, so nothing is selected. So we have every possible solutions in that, yeah, in that 1000 variation. And also for the fitness values as well, we have everything. But the selections that we have done are gone. So we have to re-export them. So we have to go to the parallel coordinate plot. I really don't remember which options we selected yesterday. So just for demonstrating today's session, I'm just going to go with one of the generations and export it. And then in the DLA, we can go back with analytic methods and selections as well. But for now, I just need a couple of phenotypes to export to our actual file. So I'm just going with the last generation because we already know that probably it has the most finite values in terms of our evolution. So let's click to export. It's going to take a second. Once it's finished, it says it export finished. Oops. Okay, so right now we should have something in the phenotype. Yes. So you can see in our path, we also have the kind of order because we know that we already exported our last generation, which is the 49th, right? And when we are having our phenotype solutions, it's keeping that identity and giving it a certain order, which is quite nice because when we are trying to match our phenotypes with our genomes and fitness values, it's quite important. But also, as you can see, this is not a version that we can directly use because this is a kind of data encrypted. So we have to use certain components in order to extract this data. So the first thing that we are gonna use is called decode phenotype. So this is in the Wallacei tab and Wallacei X. You can see we have 3 other components. I mean, this is the Wallacei X, the main component, and the rest of them also pretty useful. So we will go through them. Let's first start with the decode phenotype. So once we plug our phenotypes to Wallacei phenotype input, this is automatically the display is off in terms of having bad performance issues. But when we input our phenotypes into decode phenotype, it automatically start to create data, not in this way, but let's say if I have a mesh, you see I have a couple of meshes. Although we know that I already exported more than one phenotype, right? We have from 0 to 19. So we have 20 different set of mesh here. So what we need to do is we need to explode the tree. So this is a mesh tree in a way. And we have an error, right? Which says tree contains more branches than this component has. So there is this very easy operation. If you right click and say match outputs, then it will create outputs with the same number of branches that we have. So let's close the preview. And now what you can see is now we have each phenotypes that corresponds to the list that we have. So this is the 49th generation and first individual, and this is the in the same generation, last iteration. So we can scroll through them one by one like this. But when we open it, we have everything together. So this is not very useful for us. So instead, we will going to be using like this. So this is the, let's say, the first method to extract our phenotypes. Let's put it here and let's call it first extraction. And let's leave it here. Okay, there is another cool way to quickly navigate through the solutions. For that, this time we need to create a list. But first, so we already have the mesh list, right? If we join this meshes, we have all of them together. And if we list them, and if we create a slider, which is in between 0 and 19 again, because we have 20 generation in that list, right? And if we put it, what I want is when I change my index, I want to go through my individual selections, but let's check from our data weaver. But you see everything right now, it's in 20 different branches. So in that case, obviously I can't go through them, so I need to flatten this. And let's close it. And now you can see I can go one by one, just sliding my slider. This is also a useful method if you quickly want to navigate between different solutions. And let's also put a custom preview here. Let's put a color. Yeah, yeah. So also, in case you haven't used it before, there is this animate button here, which allows you to create like image files from your interface in Rhino. And this is also quite useful if you like to create like animated GIFs or videos with your, let's say, generations. So you can just right click on it and select location. Let's create an animation folder. And you can say, I want 20 frame. I think first we need to arrange it a bit better, I guess. Okay, let's say 20. It's in parallel, and you can change the resolution. Let's keep it like this, and you can include even tags, like it will add some information in below. We can also unclick this, and once we say OK, it will go quickly. And then let's check what we have. Animation. Didn't we put it there? Okay, let's check again. Maybe in the second time I didn't put it there. Yeah, it's in a different place. It's in the Wallacei folder. Okay. Yeah, I mean, I couldn't arrange it very well, I guess. But if you put it in the middle and then if you animate it, then you can have each frame, and then you can either use a third-party program, and then you can create your own video or GIF or whatever. This is a quite useful tip as well, I think. Okay, so this is the second way of, let's say, visualizing or exporting our results. And also let's give a title to that. Let's call it listing. Okay, so right now, as you can see, we only extracted our phenotypes, which are the results, like the evaluated and generated throughout the time in our optimization process. But we also want to see the actual effect of the optimization process, right? Because as we speak in the previous session, we said that the values, which are called the fitness values, are the real indicators. Either our design solutions are improving or not. So therefore, for learning that, we also have to extract those data from our output panel, right? So what we need is, first we need our fitness values, and we need to match those fitness values with our phenotypes. Therefore, we can understand which design solution is the one that we are looking for, and which kind of design solution has some positive effects in which part of our, let's call our aims and criteria or whatever. So in order to extract that, first let's check again what we already have here. So you can see we already have all the fitness values in our optimization process. And on the other hand, in the phenotypes, since we exported only the last generation, we only have the last generation and its path, right? So what we need to do is we just need to have these fitness values and match their paths with the phenotypes, right? So there is a very useful component for it, which is tree statistics and tree branch. So if we have our phenotypes as our tree, we can extract the path. Let's check what it gives us. You see, we have one branch, and in this branch, we have our data paths, which are the ones that we're looking for our fitness values, right? And as tree, if I put my fitness value and if I match those paths, you see that right now in my fitness values, I also have the same variations, right? So it's clear till now, right? Everyone is, I mean, I don't know how familiar are you with tree statistics or branch and everything. So if there is any unclear parts, please stop me and ask questions, thus we can go through them again. Or it is very early Sunday morning and no one wants to join. It's also welcomed as well.
Can you maybe put panels on tree statistics as well, and tree branch? Like, can we see the
Okay.
change?
So, yeah, of course. So we can, let's first even put to our phenotypes and then put it to our tree. And we can now see how our, oops. So you can see that we have the same path, right? This is not changing anything. This is just extracting the path that we have in our phenotype output. But in our fitness values, you can see this is a different path. This has everything inside. So, but when we put it as tree, in the end, we only have this path here as extracted. Maybe it is clearer now.
Thank you.
Thank you. Also in the chat. Okay. Thanks, Louis. Okay, so we have extracted our phenotypes. We have extracted our fitness values. Let's also extract our genomes, which are the changed values from our genes, right? So we had, as a initial configuration, we had some kind of configuration in our genes, sliders and everything. But then, of course, for creating new generations, the evolutionary algorithm played with those. And now we don't know the new genomes, new gene values. So we also need to extract them. So as you can see, it is kind of similar with our phenotypes panel here, because it also has its own way of keeping the data. So this wasn't the case in fitness values. You can see in the fitness values, we could directly see the results, but in genomes and phenotypes, we can't see that. So what we did was, in the genomes, we used a decode phenotype, in the phenotypes, we use the decode phenotype component. So also for our genomes, we need to use something similar. But first, also let's put a name here. Just not to mess things up. Tree statistics for fitness values. Okay, so what we need to do is basically the same thing, but we need an extra component. So we can just copy that. And then let's take decode genome. And this time, instead of fitness, I will go to my genomes and put it to my tree. And you can see now I already match let's put it in the middle. Maybe make this a bit smaller. Okay, I already extracted the ones that I exported from my optimization panel. But in the end, I also, okay, maybe first I need to do that, and then I can put a panel. Okay, what is the problem? Invalid cast string. Interesting. Okay, let's.
I think the previous panel also converted the string.
Yeah, I think let's first remove the panels and try without them, right? Okay, we, as a path, we have this, our phenotypes as 3, and our genomes as, okay. So I'm not quite sure what it means. So, but when we don't have the panels, I mean, we can add the panel at the end to see what is the result, and also add this to our group. And now we have our genomes from our export list. So the genomes are a bit complicated. I mean, not complicated, but their way of, let's remove it for a sec. Listing is a bit different, right? Because we have a lot of gene values, and they need to be in a certain order. Therefore, when we want to reconstruct our phenotype by manually, we need to know which value is corresponding to which gene or slider, right? So this is a, let's say, in here, we'll see developers, I think they left users a bit free, because what you can do is, or you can really improvise how to do certain things. But what I do is, first I go back to my Wallacei panel. And here, if you right click your genes, and if you come to disconnect, you can see that all these genes, I mean, all these sliders and gene pools are connected in a certain order. And this is, I think, whenever you like right click and select all sliders, all objectives, it will create the same order. So what it will do is, first it will plug the sliders, and then it will plug the gene pools, and then it will sort them according to the alphabetic list, right? And with this, thanks to this consistent listing method, we know that everything in our in the top of our list is a slider, and then we have our building count, and then our courtyard area X and Y. So if we, for a second, if we change this display to the hidden, and if we go all the way back, so right now here in my canvas, I didn't order it in the same way, but I know that right now, since I checked from my Wallacei panel, Wallacei component, the first value is my slider. So this is the slider value, which is the corresponding solution of phenotype generation 49 and the individual 0, right? So ideally, if I put this value to my slider, and if I put all these other values to my gene pools, I need to be able to reconstruct one of my solutions that I'm looking for. So we are going to be testing that, but let's for a moment leave it here. And this is important because let's say in this example, we know that if I go all the way back, and this was my, yes, courtyard area X, and this is the courtyard area Y. So I know that if I reduce my X and Y values, my courtyard areas will be minimized, right? So this is pretty straightforward, but in some of the other examples, for example, in the next session that we are going to be working on, we are not going to be very sure about the effects of the changes that we do. So in that case, the optimization algorithm will be much more important for us. So at the end, when we have our genomes and when we go back and when we reconstruct them, we are going to be learning something, right? Because we can say that, for example, let's try to think about our DLA algorithm. Right now, we don't know how it is creating an urban fabric and everything, but we are going to be using our parameters that we developed there, like our sticking radius, our like number of particles and everything. And I'm not going to be really sure if I change my sticking radius, how it will affect. Is it going to be giving a feeder solution or not? So I need to know at the end. I need to somehow able to reconstruct my phenotype by manually also putting my gene and slider values as well. So that's why it's important. Okay, so let's also leave it here and put it as a default and add to our group, and also call it pretty much the same name, but this is the fourth operation and this is for our genomes. Okay, so before reconstructing our one of the phenotypes, there is one thing I would like to do as well. Probably I will mess things up every time when I try this. It's getting a bit complicated, but let's try and see. So what I want to do is, you see that now I have each individual solutions here in my phenotypes, right? And for fitness values, I have everything as a list, not as an individual. I mean, I can sort this list or I can extract the data from here. That is a method, but yeah, not right now. I don't have it. And also for my genomes as well. So you can see everything is together. But I want to have like one configuration where I can navigate through all of them at once. Like I want to, let's say, just change my mesh input and have my phenotype and the corresponding genomes and fitness values to that solution. So let's try that. First, I'm going to be copying that. Okay. Now I'm going to be cheating a bit. So what we know is we can use our tree statistics, right? So then why don't we do it again? Like we can have tree statistics and tree branch, was it called? Yes, okay. And we can match the paths which are coming this time. Instead of having our, first let's put a relay, instead of having our tree from the whole export list, we can have it from an individual, right? So when I change this, my path will automatically, let's see, my path will automatically change as well. So let's first close this guy and have this mesh. Okay, so this is the mesh and this is the corresponding path to that mesh. So this is the, I mean, phenotype. Okay, and as tree, let's go to our genome and have it as our tree. Okay, obviously we have a problem. We always have a problem. And what it says is the path 49, 10, and 1 doesn't exist within this tree. Okay, this is something expected because you can see that when we decode our phenotype, let's first check the existing condition first. Let's go back all the way. So this is our phenotype. Oops. Let's, yeah, enlarge it and copy it. I mean, we don't even have to copy it. So when we normally have our phenotype, our path is 2 digits, which is the first one is the generation and the second one is the individual. But when we use the decode phenotype, it is changing our way of creating paths. Like in our path, now we have another individual, which means basically nothing in this case because it's always 1 and it doesn't correspond to any data. So that's why in the genome path, we don't have anything like this, because if we go all the way back, also have our genomes, see, we don't have a third path in our genome data structure. So there's 2 different ways to solve this issue, which this can make more sense even. So we can first try to explode 3 and then decode phenotype and then match the trees and data and everything. But there is this one really cool component. If you don't know, I would like to see that, show that to you, which is called path mapper. So what it does is when you have a certain kind of path type, you can manipulate it. You can either add a new layer to your path, or you can remove some of the existing maps, sorry, the paths from your data panel. So first, it has a certain kind of language. We need to use brackets, and let's call our first like variable as A. Okay, let's first also put what we are changing here. So for example, this guy. Okay. So we have 3 variables, right? So let's call the first one A, second one B, oops, and the third one C. But in our data structure, we only need 2 variables in our new path. So instead of A, B, and C, if this converts it and if it eliminates this unnecessary variable, then it will be much better for my listing. So let's check if it does it. Yeah, so this is what I want. And right now, if I put my path here and this time put it here, okay, I still have a error, and it says the path doesn't within this tree. Okay, this is interesting. We are not putting that path. Why we are having this? Let's try to recompute first. Okay. Tree branch. So our value is still same. We didn't change really the value.
Maybe if you put the path mapper before the explode tree.
Let's check what we have before it. Yeah, that might work. let's try. Oops. Okay, yeah. That seems more reasonable. And let's go back to our genomes. Yeah, perfect. Thanks for the backup. Okay, let's remove this from the group and extend it a bit. Okay, right now, this is the phenotype, and here we have the genome. Of course, we need to decode it again in order to see the result. Yeah. So right now, what I know is if I change this, my phenotype will change, and also my genome values will change according to that individual. So I don't have to look for it somewhere else. I always have it here. Okay, let's do the same also for our fitness values. So let's copy it, of course, this time without genome. And this time, let's go all the way back to our fitness values and put it to our tree. And we have our we have our fitness values as well. So this is a kind of result that I want. I have my phenotype, I have my genomes, I have my fitness values, and I have option to navigate through them. Okay, let's also group all this operation together, and let's call it, this is the fifth one, I guess, right? Match paths, or maybe the sixth one. I don't know. Okay, fifth one. Okay, cool. Okay, match path. And let's close the display. Okay, so let's say I looked through a couple of solutions, and I was really curious about the generation 49 and individual 16. So I want to reconstruct that solution by using my genomes. So I will have this, I will copy this and close the wire display. And I will go all the way back. Right now, I'm not going to let's say, performing in optimization or any kind of other thing. Therefore, I can take everything which help me to create my phenotype. Then I can copy everything in a below. And then by the help of that list, by changing my genes, I will try to get the exact same phenotype. So let's try and see, okay? I already knew that the first one was corresponding to my slider, which is already in the same value. And then let's also be sure that which one was the second, but I guess it was going alphabetically. So building count, courtyard X and courtyard Y, this should be the exact same order. So let's change our gene pool starting from 14, 7, 8, again 8, 9. So I'm not going to say each individual out loud. 7, 7, 7. 6. So we can already see that we're on the right track because the values are quite close in here, and now we are jumping to 60. So it should be this gene pool. Oh, I'm having a problem with my computer. It's not charging. Just a sec. I was about to lose my laptop. All right, crisis solved. And okay, I have another case. I forget where I was, so let's try to find the trace. 31. Okay, I think I was here. This is going to be 40 and this is going to be 32. Okay, let's start from the end this time in order to not have any problem. 35. 5, 2, 50, 23.
I have a question.
Yes, sure.
Is there a way to automatically split the list and match the gene pool instead of manually entering the values?
I think there is a sublist component, or maybe it was a partition list. So when we have, let's say, a constant number of genes and sliders, I think once we can do that operation, as you said, we can we can divide everything in the list in certain amount of numbers, and we can put them as inputs. Obviously now we can't input them in here, but we can input them in the corresponding components, right? So instead of having a slider, I need to delete that slider and I need to put that list that I sublisted from my main list. So definitely there is a way to do that. But since we were going to do that only once, oops, I didn't bother with it myself right now. But yeah, that's
sure. It was just
yeah, that's a good idea. Okay. So let me just quickly check if everything is correct, and then we will see if we really did something true and we have the okay, 32, 30. Okay. Okay, it seems quite true. And now we have our display open in the same configuration, right? 49, 16, 49, 16. Okay. Ideally, so we reconstructed everything here. Ideally, when I open the preview of this geometry, they should match, right? So let's try to open it. And let's make it bigger to see. And it seems like quite matching. But just to make sure, we can use a rep wireframe for better visuals. And I think this is from the human plugin. If you don't have, no problem. Just to have a better visual. You can have a thickness. Okay, maybe it's too much, but okay. Now we can see that this is the phenotype that we reconstructed, and it's matching with our phenotype, with our selected export list, right? So this is nice because let's disable everything right now because we don't need them anymore. But now I know that if I go to my genomes and if I put them as input, then I will really have the list. I really have the phenotype that I created, and then I can start critically thinking about it. Like when okay, right now I can see that. Let's for a sec enable it. I can already see that I know that if I even lower these values, my courtyard areas will be smaller, right? This is one of the fitness values that we want to minimize. But also we have other two. So maybe when we lower these values, it's also affecting the other fitness values. So this is not the best configuration to make all these values in the lower value. So I don't know, I'm just saying, maybe this is a outcome from my optimization study. So this is where we need to come back and try to learn something and rerun our algorithm and then again compare the results. So also with the outcomes that we have, we might need to go back and say, okay, this time I'm going to change my minimum and maximum values because I might learn that 60 is too much for my generation. So it's better to keep the maximum in 50. And then I can go back and I can rerun the whole algorithm and then I can compare the result. And if I have better results, then I can say that, okay, I really learned something and I can go in that direction. And, you know, we can perform again and again. And until we are satisfied with the results. So let's call it reconstruction. Reconstruction. Okay. Let's check from the drive if we are missing anything. Okay. There is one last thing, which is distributing to a grid and a diamond chart, which is a feature of Wallacei. It might take a while though. If you guys want, we can have our break right now and then finish this stage with the final operation that we're going to do. Or if you guys are okay, we can go for 15 or 20 minutes more and then give a break and start with the DLA. So what do you guys think? Prefer to have a small break or either way is fine? Okay, then I think it's better to finish this part and then give the break. So let's try to be quick. And in any case, at the end of our DLA, we are going to be doing this again. So maybe if we have more time there, then we can go through it. Okay, so we have a component which is distribute grid, which allows us to sort our phenotypes on the Rhino viewport with a certain distance and certain analytics entwined together. So in order to do that, I think we have to put our fitness values, our phenotypes. Okay, so yeah, it already automatically create something. Let's close everything else and try to see what it is. Okay, so you can see that here we have our generation and individual as a title, which is the ID of this solution. And we have our fitness values are as listed. Also, there was a way to name them, but I don't quite remember. Maybe with another component, we can see that later. So we can also there is one important trick that we can use here. In the inputs of this distributed grid component, there is an output option, and if you scroll over it, you can see 0 is all, 1 is geometry, and 2 is mesh. So we don't need geometries in this case. The meshes are quite lighter, and you can already see the change in my interface. It's much more smooth. And we can decide to close the preview and individually also visualize them as well. Like if I can just have my meshes or just my numbers and everything. But for now, okay, let's leave it in this way. And also there is another component which is called diamond chart. Okay, diamond fitness chart. Yes. So this is the chart that we remember from our analytics panel. So when we draw here and select, let's select the first fitness value and the fittest one. So we know that here we have a chart which is visually strong, and we might want to use it in our presentations, or I don't know, in our project reports and everything. So we also like to have it in our bake list when we are going our Rhino viewport. And this component allows us to do that. Let's see where it is. Okay, I don't know where it is. It doesn't show it, but it should be some, okay, it's here, fitness chart. Okay. So this is a bit more problematic according to the grid, because, for example, some data cannot be directly inputted here. For example, if we put our fitness values here, we can't directly have, because it says fitness values per branch. And for having that, they have, in Wallacei, they have another kind of component that puts the data in a certain order that this fitness chart can read. So that's why we need that little component in between, and we need to plug our fitness values into the input of this, and then we need to put it our fitness chart. Okay. And of course we need base plane, which is the grid location of this distributed grid. Let's also try to see that as well. Okay. And of course, right now we also need the generation of individuals, and we can also put the names of the fitness criteria in this one. But we need to know the certain order for the fitness values as well. So we need to go back to our panel for a sec. And here we can see courtyard, variance, and volume. So it's again in alphabetic. So we can go back. Courtyard, variance in volume. And we need to multiline this and put to the name of the chart. Okay. We can also play with the size. Probably we will need to do that. And also we need to input how many individuals per generation do we have. And I think in our case, we had 50, right? Let's put it here. Okay, we're almost there. What we also need is we need to put our generation of individual and the individuals inside those generations. Okay, so we already used 3 statistics to have our paths, right? So we can use the same thing here. We go all the way back. If we have a 3 statistics from our phenotypes and bring it here, but oops, 10, just the panel. Okay, but in this path, I have my generation value and the individual value together, right? So I need to have them separately. So in order to, because I have 2 different inputs here, right? So in order to do that, I can first deconstruct path. Okay, yes. Deconstruct our path. And then we can list the item. And if we put another output here, so for this output, I have the generation, and for the other output, I should have individual. Okay. So this is generation, this is the individual. Okay. So I think I put everything right now. Oops. Yeah. So I should be able to visualize it, but maybe the size is a bit too small. Or maybe I put it wrong because, yes, okay, I did mistake here because we don't have 50 generation in each population. This is the this was the generation size that I put, but we need the individual size inside those generations. So in this case, this number should be 20. And now it's correct. And now if we go back, we can see we have our diamond chart here in every phenotype that we have exported. Although the location is not quite well, so we can just move this grid in X, Y, Z, right? Let's take those guys a bit far away. And instead of base plane, we can put it here. I'm not sure how much we should move them. Let's try with a slider. Okay, so this goes up, but I don't want to go down. So I can change the expression to -x. So let's go maybe 40. Okay. And also for our x component, let's go all the way down. Okay, maybe we can do it 50. Yes. Okay. So let's group everything and call it this is the 7th operation. So diamond chart and great. And let's check the outcome. So what we have our generation and individual identity as the headline, and then we have our phenotypes, and in the diamond chart we also have the notation which phenotype is which fitness value is corresponding to which cluster. Like the first one is courtyard, the second is variance, we know, and we can also compare the numbers if they are matching or not. So we can see fitness value here, and here we have the ranks and everything. So we can visually also compare them and, I don't know, print or export and do any kind of analysis after that point or use in our presentation. Okay. So I think for now it's enough. Unless you have any questions, we can give a break.
Sorry, I just have one question. Really
Okay.
sorry about that.
No.
Yesterday, in yesterday's session, you showed within the Wallacei components a sort of graph, 3D graph that was representing the result of the genetic algorithm. And my question was, what if we have more than 3 objectives? What if we have 4, 5, 6, 7 objectives? How would that graph would look like? Because it is 3 dimensions, and it works in your case because we have 3 objectives. Mm-hmm. But if we have more objectives, would it perform some kind of dimension reduction like PCA, or no? I don't know if
no, it's a really great question. Thank you for that, asking that. In the first time when I was using, I also asked that question, and what it does is it still has the same kind of 3-dimensional coordinate system, but this time it puts, for example, here you see fitness objective 1, minimize courtyard, right? And when you have the 4th option, it overlaps with this, and it puts another layer here, and it says fitness objective 4 and blah, blah, blah. And obviously right now the location has to change because there is 2 variables here, right? So in this case, I'm not quite sure how it detects the location, but it puts another kind of, let's say, color, or for example, like here we have cubes, right? These cubes are representing in this case, the Pareto front solutions in our whole generation, but it is another layer to visualize things, right? So I'm not quite sure. I don't really remember how it changed, but if you are curious, we can try to have a look at it at the end of our session, right? And we see it together.
Okay, thank you.
Thank you too. All right. If we don't have any other questions, let's give a break, okay? Do we say like a 8-minute break? 11:20, we are here, okay? All right, see you. Bye-bye. All right, we are back. So we're going to be closing that session, that part of the session, the ones that we are working with the spore blocks and the primitive optimization applications. And now we will go back to where we left with Rudvan, to our DLA algorithm. And now we will try to create an urban fabric and then manipulate it and then performing another optimization. And then in the final, we are going to be discussing what we have, how can we improve. And if we still have time, we may also try with other kind of topologies as well. So let me share my screen back first. And also let's save and close this. This is okay. Yeah, this is true folder. Let's close this guy. Okay. So let's check from the presentation as well. We did the initial extraction with decode phenotype component, and then we did listing by joining the meshes and then using a list item. And then by the help of tree statistics, we find the fitness values in the exported list, also the genomes. And we matched the data with PathMapper, reconstructed everything by using our genes and distributed to grid and diamond chart. Cool. We are not missing anything. Okay. So next step. Okay, we did it yesterday, so we changed the order. We already checked what is the differences when we have 1,000 iteration or 5,000 or 20 or 50. So we can skip to that, skip that part. And now we can go back to our DLA. Okay, so this was the checkpoint 7, right? So maybe I can prove it from Rudvan first before diving into anything wrong. This was where we left the other day. Okay. Okay, so let's download it. And then try to create an urban fabric. Oops, okay. So we have somehow when I download the file, it's in a different file format. I couldn't open it, but let's try again. Maybe because of the name, it's just.
You need to. I think it's the end of the end of the title of the file. You need to remove it and just leave it as GH file.
So like this, yeah. Thanks. Let's wait my computer to process it. It's also suffering. I don't know if you hear the voice, but it's not super nice.
Suffering.
Actually, I think that there is a filter on the Zoom meeting because I can't hear anything.
Okay, nice. Because I hear a lot. Okay. Anyway, that was exactly the same place where we left. Right? We had at the end we had our parameters as sticking radius, particle speed, maximum number of stacked particles, and initial configuration slider, which was defining if you are going to start with a point or if you are starting to with a curve. And one of them was singular point and the other was different points. Okay. All right, so first we need to create, okay, let's first, before saying anything serious. Let's first close the grid. I don't want to see that. Okay. So first things first, we have a circle that is defining our somehow the limits, right? We have our particles inside us, and also we have another circle which is allowing us to get back some of the particles closer to our work environment, right? But when we are creating our urban fabric, we want to have a static frame, let's say, and inside this frame, we want to use our points as guidance. And in this case, our which particles? Well, stuck particles, which are the blue ones, are going to be the guidance for our pattern. What we are going to do is very similar that we speak yesterday in the project that I show you. Also, we ask about it in this one. So you can see that here. If I can also get close a bit. Okay, from the second part to the third part, we were doing some kind of grids. We were creating some kind of grids and scattering points all over it. And then from those points, we were transforming our set of curves into a pattern, right? Right now, we will do something similar, but instead of using scattering points, we are going to use our stuck particles. So this is the main idea of creation for our urban fabric. So let's get started with creating our grid. And then we will see what kind of operation we need for also creating or transforming to a tile of pattern. So let's start with, I think it was rectangle. Yeah, and also let me open the bifocal first. Okay. Okay, so we need a rectangular. Also, let's put our top view here as well. Okay. So we want to match the border of this rectangular with our circle, right? Therefore, we already have a slider here. We can put it as our extent, right? So in the x-axis and also in the y-axis, we can have this extension. But since this is the radius, not the diameter, of course, this is not covering it, and also the location is not quite right. So first, we need to move this plane in x and y axis, right? So let's first have the plane of this circle as a centroid, and then move it in x and y axis. And also let's make everything a bit far away. Okay. So also I want to use that slider when I'm doing the move operation, because if I go back to the DLA, if I change my working space, I also would like to have my data connected with it when I'm doing when I'm creating the urban fabric. Thus, we don't have to go back and change anything, right? So let's put it here. But of course, this is not the direction that we want to do. So let's change it to minus. And also this change to minus. Okay. And this should be 2, right? Oops. Because as we already said, this is not the diameter, but radius. So in order to fill the whole circle, we need to put input as 2 in our X and Y values. All right. So we have our workspace here. And right now we are going to make some kind of call pattern. So let me try to explain. This part can be a bit tricky to understand, but first let's also have our cells as a separated curve and close this, and we can call it grids, or cells could stay, whatever. So let's have the center point of each grid. Okay, so let me try to draw something. Okay, so all right, so what we want to have is something like this kind of patterns for creating our buildings, right? So in this case, we're using rectangular component and very simple rectangular kind of structure. But then later on, as we speak, we can try with some kind of different typologies as well. But right now, we want to create different kind of patterns with the combination of these grids in different ways. So what we need to do is we need to do some kind of call operation, as I said. So we need to cluster these points, which are the, I can't see my mouse. Okay, which are the center point of all these grids based on a relation with our particles, right? So these particles, the blue ones, should somehow affect our clustering method. Does it make any sense? I don't know, but it may not, but when we do it, I think it will be making much more sense. So we are going to be using closest point, this one, I guess. So we're going to have our center points as our point, right? And then for cloud, we are going to be using our points coming from the DLA algorithm. Okay, and also let's make it faint in order to not make things complicated. Okay, when we do that, we have a index. And also we would like to flatten this. We don't want to mess with data structure. So we have a closest point index when we do that operation. Yes, exactly, like a Voronoi diagram. So right now we have a index which is sometimes repeating itself, right? You can see already in the number list 0, 1, and 2, we have the same index, because probably if we go into that structure, we can foresee that some of this, again, let's try to take another screenshot. So some of this, it's really hard to see my mouse here. Okay, so these points have this point as their common closest point, right? So in this case, their index will be same. So with that, maybe I can do a clustering. So I can use the points and the closest point index. And whenever I have the same index, I can try to cluster them in the same group. Thus, automatically, I can have a kind of elimination and also a clusteration, right? So in order to do that, first I need to create a set from this index. And let's also go through with the set again in order to understand what it does. So let's say I have a list, something like this. And when I put it into set, okay, I need to multiline, I guess. Okay, yeah. So what it does is it eliminates the repeating numbers, right? So we are doing the same here. We are having another, let's say, an index here. And then we need to use a equality. And we need to have this set here as our first number and the index as our second number. But also we need to be aware of what kind of structure we have, right? So in this case, it seems fine. And we are going to use a call pattern. And we are going to have our grids as lists and equality as our pattern. It doesn't do anything, maybe because of I didn't graph this. Yes, okay, so I also need to graph this, I guess, yes, in order to work this pattern, okay. So right now I did some kind of elimination in my first grid list. And now if I perform another option, which is called region union, and have this list as my curve, and let's look at that. So we have a tile of pattern, which is consisting from, let's say, random, not random, but the rectangles that are coming from the based on the guidance of our particles, right? So this is an important part of our work. If there is anything unclear at this point, let's go over through it, because this is like the main part that we need to understand, and the rest of them will be playing with the numbers, defining our objectives, fitness, and performing optimization over and over again. So is there anything clear at this moment? All clear? Okay. Okay. Nice. So let's try to play with parameters and see how the results will change. For example, let's change our sticking radius. And you see we have a different pattern. Let's change it again. I hope not, my computer doesn't crash. Okay, yeah. So already you can start to see when we change the radius, our let's say the scale is going to be affected by the decisions that we're taking here. But radius is not the only thing that affects our pattern, right? We also have a particle speed, which we have discussed before. If we increase the particle speed, it will change the relation between stackingness over the points. Therefore, it will also change the pattern as well. So let's, I don't know what is the limit, but 8 and 3. So let's try with first 3 and see the result. So it's going to be relatively slower because we are reducing the speed as well. Okay, so we have a pattern, but we can see some of the plots are getting bigger, I guess, in the border. Let's try with the highest one. Okay, now we can see the difference. I think when we increase the speed, since the particles are sticking closer to each other, in the central locations we have smaller patterns, but in the when it goes to the border we have bigger patterns. So we can keep this in mind, and for now let's put an overall value for it, like 5. Okay, it's a bit more homogeneous in this point. We really don't want to change the stuck particles, but we can also try and see how it will affect for the beginning, and then we can leave it as a constraint. So you can see this is a huge change, and we don't want to make that kind of big change because this is a completely different pattern. It doesn't even make a lot of sense. I mean, maybe in some cases it can, but the overall like variance is too high in this case, the plot variance, as you can see. And if we increase it too much, maybe it will be too less in this case, right? Yeah, we're getting more grids and less merged rectangles. So let's keep it in 400. Okay. An initial configuration slider. So right now, what we have is singular starting point, right? Okay. So if we change it to a curve, let's see how it will change. Okay, so since our particles are avoiding from the center, now we started to have a different kind of pattern, right? In the center, we have a different pattern, and on the borders of our fabric, we have a different kind of pattern as well. So let's try with the third configuration as well. And yes, now we can see there's 3 kind of clustered place where we have smaller patterns, and on the other hand, in the center and the places that we don't have particles, we have bigger patterns. Okay, let's leave it in the 0. Yeah, I shouldn't do that. I should just put a 0. Okay. Right, so this is the first function that we have. Let's call it creating urban fabric. Okay. All right, so and let's have this for good intentions, and let's call it urban fabric as well. Sorry. Right, now now we can close the display of everything here. Now we are going to be dealing with our fabric. Okay, so right now we have a kind of base, right? But of course, this is a very dense, let's say, urban fabric. Obviously, we need to have some void, some greenery, and everything shouldn't be building, right? I mean, that is a obvious thing. I don't have to say. And for doing that, we can do some kind of elimination operations as well, and it's going to be really improvising, let's say, because each time when you play with, I mean, normally and ideally, what we could do is we could work in the right scales, right? So we could say that whatever is 2 here could be, let's say, 20 meters. And we could imagine everything, every grid here are 20 by 20 meters. And as a total, we have, you know, multiplied by 20 by 35, and we would have a certain amount of square meters here. And then based on these square meters, we can give some decisions like we don't want to have, let's say, a building which is less than this square meter, and we don't want to have a green area which is less than this amount, but which also should be larger than this amount. But this is also like a very performance costing thing, because I mean, this is not a thing that you want to do in your laptop. That's why we're keeping it very small and as a test. So we're putting just 2 meter in this case. Let's say we don't have to even say meter. It's not even a right scale, but then when you actually are working on a site with the proper dimensions, you need to configure everything. You can configure everything based on your requirements, right? So we can, for now, we can just imagine like this is, I don't know, like a 2 meter 20 by 20 blocks or something. And we are going to be making these elimination operations just by trusting our eyes in this case. So we're going to be trying to be making something which is looking like a city structure, okay? So that's going to be the idea of elimination in this next process. So we are going to have each plot and their square meters. We are going to say have this area as our first number, and we will have a dispatch, and of course as list we will have our fabric, right? And this is, let's flatten it. We don't need the data structure, tree structure. And then let's first check the results. Like what is the areas that we have? Okay, let's first sort this list for a better understanding and flatten it. Okay, so we have, okay, also let's create a set, then put it here. Okay. So we have some values starting from 4 till 264. Okay. So we have a really large span of numbers, but we want to homogenize it in some way in order to have a, you know, better fabric in this case. So we don't want to have all these small amount of squares. So we're going to be eliminating some of them. So let's try to first call the ones that are smallest, right? Let's delete these and put it. And whatever is larger than will be here. Whatever is smaller will be eliminated. Okay, let's close it. Also, let's close these guys. Okay, so obviously right now they are staying in behind. We can see them, but let's say if we make it 8, did I select the wrong list? Okay, I have a problem here, but let's check and try to understand. So we have the areas. Also, maybe I need to flatten this. Okay, yeah. I need to flatten this as well. Okay, so we can see if I go with this configuration, I'm eliminating the very small ones, but I can also select to eliminate the next set of square meters as well. So it seems like, let's close this and go with this display method. From this one to this one, we have some kind of improvement, right? We have a more homogenized way of settling, because here we have a lot of small grids, which are a bit unuseful. But in this case, we eliminated them, right? Okay, so let's say this is a better structure, but still it's not enough to go with it. And one thing that is, I mean, in this case, what we do was, okay, we have this data and we are eliminating it, and then we are not using it. This is not very efficient in this case. So this is an imaginary city. So why don't we use that data as well? So we thought that, okay, we are going to create some green area, right? So rather than creating that green areas, we can already use the data that we have, that we eliminated. And instead of eliminating that data, we can merge those data and let them as let them become green areas, right? So if we use that region union, what's it called? Yes, component here, and if we put them together, we can have those eliminated parts as our maybe it's not a good way to visualize, but we can use a boundary surface instead. Okay, it's maybe this is a okay, not this is not the mistake. Let's try to see the problem here. Okay, what kind of curve with one branch we have, because we flatten it, and then what if we graphed it?
It might also be the list B. Is it list A that's bigger or list B?
Oh, okay, okay, yeah,
okay.
You're right. Yes. Okay. Okay, so if we, thanks again for the backup. Okay, so we have this area that we eliminated in the process, but rather than eliminating it, we can call it as green areas, right? And then we are going to be using those areas. Do I really need the graph here in this case? I don't need, yeah, okay. So let's leave this curve here. And call it green area. Okay. We are going to be using that. All right, so we somehow get rid of from the smaller, I mean, the smallest grids from the whole list. And let's create another curve here. Okay. But we still, let's close it. Okay. But we still haven't homogenized it yet, right? Because we have like very big patterns as well. And also, we might need some gaps as well. So we may try to find some in-between values. For example, we used here as 8 in the small ones, but we can make another elimination, like another same kind of operation here, but this time based on this curve, right? Put it here, put it here. Okay, and instead of 8, if we say like 16, let's see what we get this time. Let's close everything. Okay, so for example, let's try to have a better visual connection. Let's make it. Maybe the human plugin will help here, right? Instead of having the same thickness, we can have this geometry shader and thickness as 2. Okay, I didn't have to have it. Okay. Anyway, so what I'm trying to do is I also I eliminated the green areas. I have them right now. Let's again, for better visuals, make it like a boundary surface. So I have these areas and as my green areas, and whatever is remaining, this is, yeah, whatever remaining is now building plot, but I don't want every single one of them as building plot. I also would like to have some weights for, I don't know, like squares, you know, the areas that we have in the city. It could be anything, like we need to have meeting spaces, we need to have in between areas between the buildings and everything. So that's why we are making another kind of elimination, and then we are reducing the amount of the plot that we have, which is the secondary one, this guys. And then finally, so after having this, we also don't want to have this kind of like mega or giant blocks in our pattern as well. So once again, for the final time, let's make another operation. And this time, well, let's check the set first. What was the areas that we have? And try to the first sort then. Okay, so for example, so let's say whatever is higher than 200, I don't want to see it. Okay, this is a decision that I'm taking now, and then I'm checking if it is nice or not. So you can see those guys are bigger, but I'm not sure about this guy, why it's also selected. It doesn't make any sense, right? Interesting. Do I have the right list? Yes, this is coming from here. These are the areas, and this is the second number. Okay, this is not the correct list. This should be the list. Yes, okay. Now it's fixed. So I'm eliminating those guys, and I'm having this as my final pattern. Let's close everything that we have here, put it in a group. And let's call it elimination rather than like name, but whatever, elimination phase. And then we have a bunch of curves, which is our new urban fabric. And we have our green areas. Again, let's let's not close this boundary surfaces for better visual. Right, does it make any sense? Okay, nice. Okay, thanks also to chat. Right, normally, right now, when we are creating an optimization algorithm, what is the first step? First, we are getting a data, right? So we had the data in the beginning, which are the parameters and everything coming from the DLA algorithm. And then we have a function where we generate things, right? So this was the first step for generating our pattern. And this is the second step where we finalize our generation. And somehow already we are not evaluating, but we are putting an evolution to it before putting to a evolutionary algorithm, right? We already made a progress here. Okay, so after this step, right now what we need to do is to define our fitness values, the fitness objectives. And once we define our fitness objectives, we need to have each function that calculates these fitness values. And then we need to put our Wallacei X component again and plug everything and then run the simulation. But also before the simulation, we also need to define the limits of our parameters, right? So for example, in this case, this is going between 3 and what was it again? 5. But at the end, once we have everything, we will jump back to the beginning and we will try and see to define our these limits in a better way, because we might realize that, okay, now it seems like a nice pattern, but still this search space maybe is not enough for us. So it's better to, at the end, go back and test and everything and see the result. So since the next operation is a kind of new step, I would like to give another break here, which is a kind of, now we did a bit less hour, but because the next in the next let's say break, we are going to be performing the optimization. It's going to be a bit time consuming. So maybe it's better to have here a 5 or 6 minute small break and then go with the other functions, okay? Okay. All right, let's say a 6 minutes break and then we will come back. Right. We're back again. So I have guys come back from the break as well, just to be sure there is someone there before start back. Hi. All right. Let's go back to my screen. Okay. Cool. So let's take our time and have a very small recap what we done here and why we done this. So after we have our, by the way, as you can see, we're using fast loop as we have spoken before, because we want, okay, there's a child screaming outside. Okay, sorry if you hear that. We are using the fast loop because in the optimization phase, we are going to be needing only the results, not the operations in between. So we are having our particles as our input values here in our cloud, right? And in this cloud, we are also using our grid center points, which we created by the help of our circle and limits. We created our boundary, and then we created a set, and then we clustered these grids into their relations with the particles. And then we created our pattern. And after having this pattern, we said, okay, we have this, but this is not a very realistic pattern. Let's make some elimination and let's call this list. And we made a bunch of elimination. First, we eliminated some very small areas, and then we made them parking areas. And then we did another operation in order to have some gaps in between, like in the parking areas and in the green areas and the buildings, and in some random places over the city. And then finally, we also eliminated the the biggest and let's say unnecessary and enormously big patterns from our list. And now we have a sort of nice pattern that we can use for our optimization phase, right? Okay, also, after doing this, we have never checked how it looks like if we change any values. So, for example, how our park green areas will be. So is it working when we change the parameters? Yes, for example, you can see this is a completely different pattern. Like the green areas are scattered a lot, which is kind of nice because in the optimization phase, when we change the radius, because right now, one of the objective values that we are going to be having is the distance between each building plot and their closest park. So having this kind of diversity is really cool because, for example, in the previous part, I think it was 3, right? Let's go back and try to see. Yeah, for example, yeah, I think it's a different pattern, but it doesn't matter. So in this one, we have more central parks, but in the other one, we have more scattered ones. So we're going to be learning how this is affecting. Is it better to have big central green areas in the fabric, or is it better to have a lot of scattered parks? And of course, in reality, we could also do that, but here we're trying to keep things as basic as we can. We could define a ratio like based on our building plots. Like we could say that, for example, in this, you can see my mouse, right? Yeah. So for example, in this block, we have a certain amount of square meter, right? And we could also apply Z value, and we could say that, okay, when we have this amount of square meter, and with this Z value, we can locate, let's say, I don't know, 100 inhabitants in this place. Therefore, when these 100 people are reaching to that park, it would be different from, let's say, those guys to reach that park, because this will mean something more in the bigger scale, like because you're making more people to reach that area when you put it closer to this part instead of from this guy, for example, right? So just to give some ideas for your future studies, maybe if you need something to do. I mean, we are not going to be doing it today. We are going to just equally thread each of these plots. But this could be also something more, let's say, realistic scenario, right? So since we have limited time, now we will go in the basic steps. So let's first, as first objective, since we already start talking about it, let's try to find the distance of each these plots to the nearest park they have. Okay. So, but I'm not really happy with this pattern. Let's change it back. The other one was more. Yeah, maybe this is better since it is more scattered. Okay. All right. So we need 3 inputs. First of all, we need to have each building plot and their central points. And then we also need to have each parking areas and their central point. I mean, we could also use their boundaries. Yeah, maybe, for example, I didn't think about it before, but right now we're using their only the central locations for having a general idea what we could do. Also, we could use their boundaries and distributed our points on those boundaries. And then, for example, this guy wouldn't measure from here to here, but it would measure to its boundary as well. So, but of course, then this guy should also go here. So maybe we could project those points in some way, but I don't know. This is just a critical way of thinking. It doesn't matter as well. Right. So also we need to have a walking path in order to reach these people from one place to the another, right? So, well, we already actually have it, right? If we go back to the beginning, in our rectangular component, we already have a kind of road structure, right? I mean, I know it's not a real road network, but we can use this as a matrix, and we can say these points, these individuals can walk over these lines and then reach to these parks. You will if you don't if you haven't used the shortest walk plugin before, maybe it would be a bit hard to understand at the first place, but when we perform, I think it's going to be very clear. So first we need to have all these cells as individual curves. So we need to explode it. Okay. So close whatever we have here. All right. Now we are going to use shortest walk, which is never working in your computers and magically works on mine. This is always the case, I guess. And let's find the closest point. Okay, and first, as the point, I guess we will have our building plots. yeah, these are coming from here. So centroids are our points, and the other centroids are our cloud. Okay. And we need to have, so maybe it's better to first go over the shortest fork. So what it needs is it needs a curve, length, and wanted path, right? A wanted path is a line or a vector that is starting from somewhere and reaching to a very specific destination. So we can use a line. Also, it helps us to visualize things, right? And we can start this line. Let's first close. We don't want to have everything together. So, but we want this. Okay. Okay. So we want all these guys to start from their centroids and reach to the parks, right? So this is, yeah, this is a kind of messed up structure right now, but let's see if actually means anything. So when we put it in the shortest fork, I guess it will be giving a better result. Now, right now it's a bit messed up. So this is the wanted path that we want. And the curves are coming from the segments, which we need to flatten. Okay. So, okay, I made a mistake here because obviously we don't, okay, now I see why this is messed up, because we don't want each person to reach every park, right? Every green area. We just want them to reach the closest park. So that's why we were actually measuring the closest point. So as an endpoint, we are going to be putting our closest point, right? Okay. So right now, if we visualize it, I think it's much clearer. So you can see that all these guys have this park as their, have this green area as their closest green area, and they are trying to move here, right? And when they are trying to move, actually they are using this pattern. When the shortest walk calculates the distance, it's going to be using that. I think there's some way to visualize it as well. Yeah, so when we open the preview, it is much more clear. So let's also open those guys and give this thickness. So this is the shortest walk. Make it a bit exaggerated. Okay, yeah, this is a better way to visualize it. So we can see that when they are walking, they first find the closest segment here and starting from there, and then slowly moving perpendicularly until they find their final distance. This is pretty cool, right? I really like this component. So, okay, when we have it, also it gives us a length, which we can see here. So here we can do, I don't know, different kind of decisions just for keeping things, let's say, simple. I'm going to be adding those lengths and of course flattening it. And I have a total amount of distance, which is based on all these walks that we have. So ideally, if I have this, and also let's put a number here and call it WLC, minimize walking distance. Okay. So my idea is if I lower this value, lower this number, I will have a better located green area structure in my city, right? So let's keep this panel open. If we want to go back and see. And also we can right now have a small test and see if we change this sticking radius to 5, what's going to happen? Like, if I'm going to have a better, I guess not. In this case, it should be, yeah, you see, this is a verse value that now each citizens in total, when they need to walk to those parks, those green areas, they have to walk more. So in evolutionary algorithm, this is going to be eliminated, right? So maybe increasing the sticking radius at the end will be a worse option. So decreasing it will be a better option. I don't know. I can understand this from one option, right? That's why this optimization algorithm is very useful. So let's take this guy here. By the way, I don't know if we talk about it, but if we click Alt and then left click, then you can do this. And if you click Alt again, you can also do it vertically. Okay. So we have our first fitness value, walking distance. All right. So as the second objective value, I mean, since we are creating a kind of urban structure, we also want to reach to the third dimension also, right? So we also want to have a volume in these buildings, not just singular planes, but also something has a z value as well. So, but first let's make those faint. Okay, before moving on. Okay, so like in the previous example file, which is the superblocks, I'm going to be creating in random value for each building as well. Because why I'm doing this random number thing, I also would like to see how good this evolutionary algorithm is working when I have putting it, something is depending on completely random factor. Is it still having improvement in my design? So in other cases, you may want to define a set of rules when you are putting your z values in your buildings. For example, you can say that I have certain amount of square meters in my plots. So why don't I sort them according to their sizes? For example, this was another idea we were considering as well when we were preparing the workshop as well. I simply couldn't find time to, let's say, manage it and test it. That's why I'm keeping it simple as well. But you can say when I have this big plot, I might want to keep my floor size in 2. But when I have smaller plots, I want to have, like skyscraper kind of structure. So whenever I have something smaller, I can have a higher floor. And then you might even have a, more educated and decided kind of fabric in your case. But for now, let's, as I said, let's keep it simple and go with the randomness. And start with a series. Okay. I mean, this is not a scaled project, right? I mean, we can just try and see how it will be. Let's start with number 4. And let's also give 4 steps and maybe counting. We can, if we give a lot of counting, then it will be a bit messed up. So 4 or 5, something could be nice. And we want to repeat these data, right? Because in this fabric, we have list, if we put a list length, we are going to see how many buildings we have here. So it's almost like 100 buildings, right? Also in our series, on the other hand, we have only 4 values, but if we put these numbers in our z values, then it's going to be repeating itself again and again, and it's going to have a certain kind of pattern, which we don't want, right? So instead of that, we can first create a data structure which is consisting of the same amount of data with our building plot counting. And you see right now we have 98 number as well. But since this is coming from a series and we are repeating data, we have always the same pattern: 4, 8, 12, 16, and 20, right? So I think we can jitter it. And now our values are, I mean, complete. This is not the complete randomness again. So in the previous file, we used the Python, right? Python component. Maybe it could be also a good idea to use Python here in order to have a complete randomness. But I don't know coding, so I don't know how to implement it. Instead, now we can also stick to those numbers as well, because even though we have the same numbers, always there, when we put a seed here, let's say it's going between 0 and 99, we have same numbers, but the order is always changing. So we can count as this order also as randoms, right? So if you are not satisfied with it, you can try to change it as well. But for now, I think it's, for me, it makes the job, right? Okay. And also, let's try to put our parameters that we are going to use in our Wallacei algorithm in the beginning and call them a proper name. For example, this will be height. Oops, this is not height. Height values of buildings, right? And I put always WLC in order to, you know, automatically snap to my genome. And okay, so we have this, but this is only a numeric data, which doesn't create something in 3D. So we have to extrude everything and use these data as a vector, right? So everything here is going to be a vector. Let's hide it. And when we are extruding it, we also want this to be a closed, like a closed mesh or BREP or something like this. So we have this, we have our boundary surface, and we are extruding it in this direction, right? And at the end, we should have 90, yes, 98. building. So let's also check from the perspective. Okay. Let's go to the isometric and try to see if the better visual expression, if this is something that we want or not, because we can lower the values, can change it. So I think it's a bit too high, so maybe I can do is 3.5 and 3.5. And maybe this can be 4. Obviously, it's changing randomly. Okay. So maybe this is a better, fabric, right? So, I mean, since we're improvising, there's no real criteria here rather than what we see. So I believe this is something that we can go with it. So when you're trying, you can try to find your own set of rules and everything. Okay, so let's go back to the canvas. And there's one thing really important. So when we do these kind of operations, you see that always my profiler is open, because every operation that we are doing in the evolutionary algorithm is really important. And if we really don't need to have it, we have to disable it, because you can see that this is a time-consuming operation in the Grasshopper script. And this is not really, I mean, we can think that this is contributing to our workflow, but this is not actually contributing, because in order to have our building heights, we really don't have to construct them. We just need those values, right? I mean, we really don't have to construct them each and every time, because when we are going to put this into evolutionary algorithm, what it is going to do is, you know, it's gonna change something from the genome, from the genes, and when something changes from the genes, all these operations are going to be repeated. And some of these operations are quite light. You can see like they are not really time consuming, but when it comes to especially the solid operations, if we can disable them, we are going to be disabling them. So in this case, I'm going to be disabling them all, because in the beginning, I'm not going to be needing them. And then when I go to the exporting phase, you know, if you remember in the beginning, we also don't put our phenotypes in the Wallacei component, right? So when we have this, we only have to put our genes and objectives, actually. Even the data is not, I'm not sure, but it may not be necessary to put it in the beginning. We can test it out. So that's why I'm disabling this operation in the beginning, okay? But I mean, my initial idea was to have a volume and have this extrusion and then have the volume calculation from here, and then minimize the volume of this this creation, right? But since now I don't have it, I need to find another way, which is pretty simple. So if I have the square meter of each of these plots as my number, right? So let's visualize it. So this is the area. And each of these values, when they are going to be multiplied with this number, it's going to give us our volume, right? Because let's say this is a 10-meter high building and it has a certain amount of square meter, and when we multiply 10 with this number, we have already our volume. And if we multiply everything, and then if we add them in together, then we are going to have our second fitness value. So what we can do is we can have our values, which are constructing our unit vector, right? The factor z, and we are going to multiplying them. And let's see what we have. We should have 98 building volume. Okay. And we will add them together. And this is the total amount of volume that we have. Okay, so rather than going from this, this is a much feasible way and much efficient way to go with an optimization algorithm. So we should always need to learn this kind of mindset in our studies or research or whatever. And we need to make efficiency maximum. So let's also call it minimize volume. Okay. Because I don't want to have giant buildings. I want to have a smaller amount of fabric, equally, like more or less in the same kind of structure. Okay, so this is our second objective. Is there any question also in this part before we moving for the third objective that we are going to create?
I'm sorry, I do have another question.
Yeah, go for it.
I'm really sorry. It might sound stupid because I'm not an architect, but why are you trying to minimize the volume of the buildings? This is the first question. The second one is, why are you trying to minimize the volume inside the genetic algorithm? Because you could just lower your input values, for example. You could you could constrain your input values and have small height values. Why do you need the genetic algorithm to do it for you?
Okay. Okay. Good question. First, let's start from the second one. As you said, this is obvious that if we lower the input value, then we are going to be decreasing our volumes, right? This is something that we know. But first of all, the first answer to that question is we are trying to understand what is the idea behind of this genetic algorithm, right? So if we know the answer already, for example, in this case, we know that if we lower the gene values in our script, we are going to lower our volumes. So we want to keep track of this when we perform our genetic algorithm. So we want to see that how close the genetic algorithm could move in certain amount of iterations. So we can say that, okay, for example, for walking distance, I don't know what kind of initial configuration I need to do, right? But for the volumes, I know. But this is, let's say, some kind of indicator that we can control. I mean, even though we have all these graphs and everything, this is kind of second, we can say, a control mechanism that we can check. We can try to see if it really makes, if it really performs a nice evolution in the process, and let's say how close it went. Like, let's say we have a, I don't know, let me try to give you an example. If I have building heights in between 10 and 50, I know that if I put 10, it's going to be the lowest amount of volume, right? But when I actually apply the genetic algorithm, at the end, I'm going to have the genome values that I can compare. And when I look at my genome values, if I see that it's, let's say it's in 30 in the best possible result, right? When it tries to find the fittest value in the, let's say, in the result, it came up with this kind of number. And then I start to question myself if this algorithm really does its job or it's not. So this is also a topic that we need to be critically thinking about it. That's why we are also adding an obvious thing that we know. I mean, on the other hand, also, since we put a randomness here, we actually right now don't know how we can minimize our volume, right? Because this is based on a randomness. So I don't know which seed option gives the best volume result as well. So, you know, we can try and see the both if it answers your questions. I don't know.
Can I also say something? So
yeah,
there might be a case, for example, that you have constraints coming from the outside. Like, for example, if there's zoning laws that say all the buildings have to be between 3 and 5, then you might not have the option to manually reduce the height. In which case you have to rely on the genetic algorithm to figure out for you what the configuration is, right? So here we're putting the height, but it could be that the task is given by a client, given by the city or something that actually has more constraints, in which case you might not have the option to do it on your own. And that's when it gets difficult to kind of figure it out without this kind of algorithm.
Yes, that's also a good point. And I'm sorry, I forgot about the other question. Can you repeat it again?
Oh, it was a really basic question. It was why as an architect do you need to lower the volume of the building?
Okay, I see that. Yeah. Yeah, in this case, we really don't need, but this is also like to keep the scenario together, right? We are trying to understand what can we do in the limit of this algorithm, and are we really doing this? And if it's based on the randomness, how it reacts, and if we know if we do this certain amount of operations, we're going to have this fittest value, and if the genetic algorithms is also capable of doing this, that's kind of an indicator that we selected for this case. And otherwise, there can be, I don't know, an application, as Rudvan said, based coming from a client or based on some requirements. We might need to be, let's say, we need to solve a design issue with a possible of least amount of volume. There might be a case for it, but I mean, I can't come up with an imaginary scenario for now. Okay, thank you too for asking. And they're interesting questions, so no worries.
Yes, and we also talked about these kinds of stuff when we were preparing it as well. So it's legit questions.
Yes, and also one thing I can add, in the beginning of this workshop, we were also considering to maybe we can try to lower the solar radiation between all these blocks, right? So in this case, maybe we might want to keep the total amount of volume, but we might need to change the configuration of them. Thus, we could see that, for example, if we have a higher amount of floors in the central location of the building, in the overall solar comfort of the city, what kind of result we will have. So this, for example, in this kind of scenario, also volume could be important, but then it could be a constant, not a variable, and it could be the orientation of the volume, the distribution of the volume could be variable in this case. So we could keep a range for the volume. For example, we could say the total amount of volume will be between in these let's say numbers, and we want to have this solar radiation as a target. We want to minimize it. So let's try to play with the volumes and see how it affects in between regions of these streets. But it's a very performance consuming thing. So then we gave up with playing with those kind of environmental analysis. But if you're curious, and at the end, I can also show a couple of sources that you can use and easy to implement your design as well.
How are we doing on time? Or do we?
I really lost track. I'm not quite sure. But okay, let's try to figure out together. Right now we have 2 fitness values. We are going to create another fitness values, which is the for having a better urban fabric. We're going to be trying to minimize our variance in the plot sizes. So it's not a very time-consuming thing. We just need to write a function. And then once we have our variables, we are ready to make a optimization study. So maybe it's better if we can hold on until we have our Wallacei X component, and for the next break we can start our evolutionary algorithm, and then when in the meantime when the computer is running the simulation we can have a break, because otherwise, I mean, it can take a bit of a time, like it can be a longer break. In this case, we can wait for the computer, right? Okay. So, all right, so let's try to be quick in this case. And then for Louis, after we run the algorithm, we can also add a 4th fitness value and try to see how it will be in the graph in the Wallacei interface. First, let's do it for 3 fitness values. And because we already did, and we can have a comparison with the existing results, and then we can try with another one. Okay. Okay, so let's try to be quick then. So we have those 2. Okay. So the variance is the term that calculates for each individuals how they are far away or close to the mean value. So in this case, let's say the mean value for the area is, I don't know, like let's check what kind of square meters we have. Let's say 48 is the mean value. So we want to push this plot to be in the almost be in this mean value. Okay, so for this we have a term called variance. If you just Google it, you can see how it is calculated and everything. And why do we calculate in this way? So, but for now, let's we try to also implement it in our Grasshopper script, right? So let's have the, okay, we already have the area, and we have, let's call these areas of each value, values, and try to, I mean, let's flatten it in case we have any problems in there. And then we need to also, okay, let's do it like this. We need to also add those values to each other. And we need to also have the list length. So we need to know how many values do we have in this list. So the building count. And we need to have a division, which is coming from the total of each values and the list length. So this is the mean value, right? So this is 30 is our mean value apparently. And let's call it M as a mean value. Okay. And also have the others as number as well. So this is total as T. And this is the N, like the how many variables we have in this, how many buildings we have in this operation. Okay, so we need to write an expression here. Okay, well, this is not a kind of expression if you want. So how we calculate this, we need to first sum the list, and we need to sum from this operation, we need to have a secondary operation inside this summary. So we need to have, from the total, we need to extract the mean value. And we need to put a square. And I don't know how to put it. Okay, I should really practice it. Okay, I'm gonna cheat and try to have this from my another equation. Yeah, I don't know how to do that. So if you share with me, I would be happy. And then we need to divide it to the total amount of variables that we have. And let's have a preview. Unknown variable in count, of course, because we don't have T, M, or N. So we need to configure it. M and also N, right? And this is our T, this is M, and this is N. Okay. And let's go in. No syntax error detected. Okay, nice. So, and also, I think this is the standard deviation. So we have to have the square root of it. Also inside the expression, I don't know if we have this, but I mean, yeah, I don't know. So I'm putting it outside. So this is the variance that we have. So in order to understand it better, we can try with different set of numbers. Let's create a list. Let's say 12, 20, and 22. Okay, and if we have the same list with a really big of number, if we multiline those guys, and if we have this guy here, okay. So instead of areas, if we assume that those were our areas, the buildings, so ideally this should have a much bigger variance, right? So let's check. So this is the variance of this list, and this is the variance of this list. Okay, so I think it should be clear now, if it's not before. So let's also have this result and disable everything and put it in another function group and call it plot. Oops. Plot variance. Okay. And also for this guy, WLC, minimize plots variance. Okay. So we created our pattern, we eliminated, I mean, we educated somehow, and then we created our objectives and fitness values, right? Now we can go with the optimization phase. So we can directly select our objectives. We know that. So when we right click on it, it automatically finds any number values that we put WLC in the beginning. And for the genes, we haven't really decided yet to them. I mean, we put WLC only to height, but also we want to have our sticking radius as a component as well, as a gene value as well, and also our particle speed, and also initial configuration slider. So in this case, what we are trying to figure out could be which configuration is the best in these fitness values, because when we generate a lot of generations, at the end we can compare that. Maybe we are having the fittest results in the singular point, or maybe, or it would be unlikely because we need to scatter the green areas, right? So maybe starting with 3 different locations would be the best result. So it would be really interesting to discover that. So that's why we're also putting this as a gene to our optimization algorithm. And let's select all the sliders as well. Okay. So about the limits of this sliders, we made a lot of trials before the workshop, so we have some limits already decided. So I'm not gonna explain why we did them, because I'm going to explain, but we are not going to rediscover it. So what we did was, first we tried with let's say a limit which is between 3 and 6, and then we saw that maybe when the sticking radius is 6, it is changing the scale too much. So after trying and going back and trying and going back, we realized that when it is in a range which is in between 4 and 5, this is a nice kind of, this provides us a nice kind of pattern. So I'm going to re-implement this. So it's going to be in between 4 and 5. And for the particle speed, I think we already in the nice limit. So 3 and 8 is kind of nice. Yeah, and the rest is okay, I guess. So okay, so one last thing. First, we need to also create our phenotype, right? So this is the urban fabric. Okay, we should already have it. Okay, yeah. So this is a BREP, which is our what is called. This is our buildings, which are going to be constructed when we open it, but now we don't have it. And also we're gonna have a mesh copy of it and entwine it. But of course, right now we don't need to have it. And additionally, at the end of this operation, I also would like to have my parks as a phenotype as well. So I want to keep them. But for now, I also don't have to create them. Let's call them green area and put it to my branch. And those are the buildings. And these are the buildings mesh. Okay. So, okay, I broke something. Okay, I was using the boundary surface. But do I have to use it so I can also calculate from the curve itself, right? Yeah. Okay, there is an error, but I know actually because sometimes these walks are overlapping. Yeah, it actually performs, but sometimes the park starting point of a building and the park in the same places, so it gives an error, but actually it works. You can see in the panel we have our results, so it's not a problem. Okay, so okay, we also get rid of from creating an unnecessary operation, and all our values, let's check. Are they working? Yeah, we have a value here, here, and here. Okay. And we have our phenotype and data. For data, we can put anything as we already talked. So let's go with the area of our buildings. But of course, let's not have thousands of data when we create everything. Instead, let's have the total amount of, yeah. And also make this a number. I think also we can use data component. And let's call it building square meter as data. Okay, and then let's save it. And let's jump into Wallacei. Okay, so now we're going to start running, and then we're going to give a break. In order to understand how much time we need, let's have a quick test. So how much iterations can we produce in that time? In my previous experiences, I know that we can't, in this case, we can't really iterate more than 1,000. So first, let's try when we say 1,000, how much minutes we're gonna need. So let's give a bit of a time to estimate how much time we need. Okay, now it says 1.5, but I think it's gonna reduce. Let's wait for a minute. Okay, it doesn't seem so bright. Okay, it's not the best day for my computer apparently. Okay, let's stop it. And also let's try to see if we can change anything and make this operation quicker. And why do we have this?
I think it's the panel again. The
Ah,
panel converts it to string every time. I'm not sure though.
Yeah, I hated panels in this series. Okay. So let's check if we have any unnecessary operation, but obviously we need to, in order to have region, I mean, we are not directly, no, we are using it. We are having these areas first, and then we have this input, this output as our input. So we can't close it. We can't close any calculation. I mean, they are not consuming time though. Also, let me try to close every other file that I have in my computer so I can't cheat anymore.
One thing maybe, how many points are we using in the DLA? Oh, we're using 500, right? If you go up slightly. In the divide curve, yeah. If we do more than 500,
oops.
Maybe it's not good. Maybe, yeah, that's fine. That's
okay. Okay, so do we also try to lower them in order to, you know, but
yeah,
maybe...
I don't know if lowering it will increase or decrease the speed, because the more particles there are, the faster it should go, but then also it takes longer for the computer. So I really don't know.
Okay.
I think we can keep it.
Okay, I think let's keep it and go with maybe 500 or 400 iteration, really with a low amount of iteration, because in Drive we also have a result with 2000 iteration or something with the same configuration. So if we change something, then it won't make any sense to compare with it. So let's have less amount of result, but with the same kind of iterations, right? Okay. And just to make sure if you're not missing anything, double check, because since it's going to take some time, we don't want to go back and now we need to reconstruct this and something like this. But everything seems fine. Every genes are fine. Also, I think, okay, this is already disabled. Okay, I think we're ready to go. Okay, let's lower it to 400. I think it's not going to be optimizing anything with this amount of iteration, but at least we still can see the general behavior. And then check with our other file. Okay. So let's again try to start. And when you start, when you click start, you can see there is this minimize Rhino on start. This is also for the performance problems. So always keep that ticked and start. Okay, so 20, 25. Okay, so right now we can give a break for 20 minutes. In the meantime, it can perform this simulation. And when we come back from the break, we are going to be going to the final phase of our workshop. We're going to check the results, analyze them, and if we can have any outcome from them, we are going to have. Okay. So, okay. Do we have a deal? Okay. Then, okay, see you in 1:30 or 1:35. Okay, whenever it finishes. Okay, we are going to be seeing that on the screen. I'm not stopping the sharing. Welcome back, everyone. Let's give a minute for those who haven't come back. In the meantime, our simulation has finished, and I would say for 100 iterations, the overall, I mean, in the parallel coordinate plot, it seems quite nice because we can see that throughout the time, you know, these red curves, which are representing the solutions, are getting fitter. So we are getting closer in our fitness objectives, which is quite nice. And let's dive into analytics to further on analysis them. And also we can have a snap of it with the entire population. So we can see that it's getting fitter and fitter. And one thing which is quite nice is we don't have any null solution in this case, because I remember that when I ran the algorithm, when we were preparing the workshop, I had some null solutions. So maybe this time I created a cleaner, let's say, script. So I need to go back and check what was the wrong in my case, and this time it's true. All right, so let's dive into the analytics. Okay, so in the fitness value chart, we can see that some fitness values are better, let's say, fitted according to the others. For example, in the volume, we can see that the later generations are almost in the closest point of the x-axis, but also like the walking distance seems quite fine in general for 400 iterations, of course. But in the plot variance, it's not so clear what's going on. I mean, in the trend line, we can see that all of them are doing something nice. So I'm quite happy with the general result, because right now I know that if I run this algorithm with 2,000 or 3,000 or 5,000 iteration, it's going to be much more. It's going to give me much more better results. But for now, let's select some of these solutions. For example, the fittest solutions in terms of each fitness objective, and add them to our export list. This is for the volume, add it, and this is for walking distance, and add it. Okay, so also let's go to the selection panel and use some of these analysis methods. For example, I can also select the one that has less amount of relative difference, which is not quite nice. You can see it's in the first generation and the individual 6. I know that in the first generation, I'm not going to have a really nice result. So I will try to go with a higher relative difference between the fitness ranks. So maybe in the later generations, I can also have some results. For example, already this is a better result. Even this is a better result. So if I go a bit further without, having this curve too inclined, so maybe this, or let's try a couple of more. Maybe try with 10. Okay, let's go with this one as well. So I'm gonna add it to my export list also. And let's go with the Pareto, Pareto-Front solutions. which are the non-dominant solutions in my generations and the individuals. And it's interesting that already in the in the generation 1, but in the second list, because we start with 0, we have a Pareto fraud solution as well. So let's add all of those. Maybe we can also, because we don't have anything from the latest generation, right? Okay, so we can also add the latest generation in our export list. And I think we can export those guys. So I don't want to recreate all these scripts again and again. And so let's go back to our superblock files and use that we already created in the previous part of our session. If I can find it. So this file, let me check. And of course, in the meantime, we should also enable our phenotypes, sorry, because when we are exporting, obviously we should be able to get the data of them, right? Okay, we don't have, okay, because we didn't enable it. Okay, so we have them right now. Let's close the display. And also we should simplify it in order to get rid of from the complicated data structure. Okay, so this is not the file that I'm looking for. Okay, I think I found it. In the meantime, I can start exporting. And once I have, okay, let me also be sure I have everything. Okay, I have genes, objectives, data, and phenotype as, and fine. And I have building as rep and mesh. Okay, I have everything. Let's export it. Okay. I have 30 phenotypes. Let's see how much time it will cost. I hope it's not gonna take a lot. When we can see that, for example, here we are creating 30 options. Let's say it's gonna take 2 minutes of time or 3 minutes, but in 20 minutes we created 400 generations. So if we would, I mean, I talk about it a lot, but you can see that here as well. If we would have them enabled, I mean the phenotypes, then the whole procedure would take a lot of time. Instead of 20 minutes, maybe it would cost an hour. Okay, in the meantime, I'm also looking for my file, but I couldn't find it yet. I mean, we are waiting for the export in any case. Doesn't matter. Okay, I found it. And where is my Wallacei path? It's here. Okay, exporting has finished. Cool. And let's copy what we have from the other file to our new file. This is not the one. Okay, this is not the one, right? I'm having a bit of an issue with my organized way of working. So not this one, but okay, this is the final file that we have, right? Yes, this is 400, and let's keep it here. I think I copied everything that I need and pasted. Okay, cool. So these are all the operations that we did in the previous session. And now I'm not going to use all of them, so I don't want to use those guys, for example. Let me also check if this is the correct. Oh, okay, this is not the correct one. No, it is. But didn't I plug the phenotype, maybe? Let's try to see. Okay, this looks like what we have, right? Yeah, this is the one. Okay, apparently I didn't plug the phenotype. Okay, I need to rerun the export. I don't have in my export list, so let's go back to quickly draw and select. Okay, we can add it. Okay, and selection. I mean, let's go with the Pareto fronts without first generation and the latest generation. Okay, let's export again. And in the meantime, let's close the other things. Okay. Sorry about that. Let's wait again. So we are in the last 45 minutes. Now we can analyze what we have from the optimization, and we can quickly try to understand if the initial configuration has an impact in our design. Like, let's check the latest. Let's first visualize everything on a grid, and then let's try to visually also separate green areas from the buildings. And then let's check the genomes and try to see if there is a pattern, for example, in the most fitted values in terms of green areas, if the initial configuration 0 is giving the best result or not. If there is any kind of pattern, let's try to find out. I also don't know the answer of it. So if we could find something, it would be very interesting. Then we could say, if we start with different points in our space, we can have a better oriented green area in our city.
That's also quite interesting for me, because we, after doing all of this urban pattern generation with our algorithms, it's really difficult to predict what's going to actually happen. And I think most cases that you're going to want to use Wallacei for are also going to be cases like this, where it's not really possible to figure it out beforehand. Yeah.
Yes,
Let's see what happens.
Yes, exactly. So I'm quite curious as well, and let's try to find the answer. So let's go with grid. Okay, let's have our fitness values, our phenotypes, and it should create it. Okay, we have it. And then again, we need our phenotypes, I guess. Yes, and phenotypes and diamond chart and everything we have, right? Okay, and also our fitness values again as an input. All right, so let's open this and this guy. And let's check. Okay, it's a bit messed up, so we need to change the sizes, but first let's get rid of this grid. Okay, let's have a look at the grid size here, size of the graphical data. Maybe even less than 1. Okay, too small. Maybe 1 will do the work. Maybe let's try to change the location. So instead of 150, oh, now this is okay. So let's try to put it under a resolution. So it's too much. Okay, so maybe just 10 is enough in this. No, it's not. So 20, and make this a bit less smaller, a bit more smaller, and yeah, put it somewhere around there. Let's call it 45, and this 15. Okay. Yeah, I think it's a nice location. And also, like, I mean, now we see everything together. It almost looks like a pixel city, which is quite nice, but this is not we created, right? If we go to the isometric view, we will see that since they are in different, oops, turn upside down everything. Let's go back. Okay, I don't know how did I manage. Let's stick in the top. Okay,
I've never seen that before.
Yeah, I'm shocked, but I couldn't give my reaction. I think seaplane also have moved when I do that. I don't know how, but okay. Okay, let's first try to see. Let's first try to see the results and their fitness values, and then we can do some improvements in the visualization part. So this is the final generation 19. You can see in overall, we can see that in the fitness value 3, we have a, okay, it's better to check the ranks. You see, for example, these guys don't have a lot of nice ranks. It's kind of overall, even not so well, these guys. But we also exported some others, right? For example, this guy had, no, not this one. Okay, these are, I think the Pareto front solutions were those guys. And I'm also trying to find the generations which are based on the fitted values in terms of singular selection. Let me check from, okay, maybe it's better to check from my Wallacei panel. Which one was that? So, okay. So if we go back and say, first, of course, we should draw it. For example, in first fitness value, which one was it? Okay, generation 17, individual 5. Let's go that. Generation 17. Okay, so it's interesting that there is no fitness value in front of it. I don't know why. It's, I don't know, maybe a problem from the software. I don't know. I have never faced with that, but also the rank doesn't seem quite right. Let me check again, because it should be the fitness value, right? So in the rank, it shouldn't be like this. So you can see, for example, in the plot variance, we should have 0 between 400 ranks, right? So this is the generation 17 and individual 5. Interesting.
Could be maybe because we copy pasted it from the other file. Maybe some of the things came with it, but it shouldn't really happen.
Well, we can try to see exporting again, like individually, and try to see in the process there has been some confusion. Also, we can try to see if there is any problem in this path system. For example, also here we should check the names and everything as well, because yeah, for example, we shouldn't give name because we know. Also, okay, now I see. Yeah, well, you said the problem correctly. When we are copying and pasting it, we didn't change this, how many individual we have in the per generation, right? Because in the previous one, we had 50 generation in each iteration, but this one we have 20. So we should change this to 20. And now the values should change, right? And now we have the fitness values as well. Okay, so yeah, and now we can see this is the most fitted option in terms of the first fitness criteria, which is, I think it was the green areas. Now we can put a name of it in order to have a better understanding. Let's go back quickly and see which is the order. Variance, volume, and walking distance. Okay. Let's put it here. Plots. What did I say? I forget. What did I say? So variance, volume, and walking distance. Okay. All right. Let's multi-line it and put 2D names. Okay. So yeah, now we can see here we have the best variance, and also I think we have some others as well. For example, yeah, here we have the best walking distance, one of the best, let's say, not the best, but one of the good ones. And also like the overall ranks makes more meaning right now, because when we first look at them, the ranks were quite high, but now they get lower. I mean, maybe not in this case, but in general, we can see that it's we are in most of the cases we are in 2 digits, You can see here variance is quite nice. Also walking distance here as well, the variance is quite nice. So this is like the for 400 options. Of course, it's not going to be perfect in the last generation. So let's try to have a better visual before making any outcome from it. Let's put it here and go with this perspective instead. Okay, maybe if I go to is isometric right now, it's not going to be bad. Okay, let's stay like this. Okay, so I want to have this, and also I want to have a better understanding in my buildings. So let's have our meshes. Oh, we already had it. Okay. Let's have these meshes. Remove from group. Okay, it really doesn't want to remove from the group. Anyway, let's have another one and leave it there. Okay. So let's open the preview for it. Give a nice building color. Okay, and also you can see that I have my park, my green areas as well, right? Because in my mesh list, I also entwine them in my phenotypes. Why I did that is obviously at the end, I also like to visualize them as well. So we can somehow find them from this mesh list, right? Because all these buildings have a z value, therefore their centers are always in the let's say move in the z axis, right? But on the other hand, always our green areas have a 0 value in our z, right? So if we deconstruct the area of these meshes, and if we find the center of them, right, some of them will have always 0, right? So let's try to see. We sort. Maybe first I should flatten. Yeah. Okay. So some of them always have 0. And I want to have a dispatch. And equality. And whatever is equal to 0, I want to have it as a different list. So let's go like this, close everything. And then have another. Okay, here I'm having a problem with my graph, I guess. So whatever I have has 52 branches, and I think I shouldn't put them into one, then I'm losing it. But why it didn't have the 0 value in the beginning? That is weird. Okay, it already did that. I don't know when I sorted it, why I didn't see them. Anyway, so let's have them and have them like this. Okay. So, okay, right now we have everything, right? We just need to check our genomes and try to figure out if we have a pattern in terms of initial configuration. So first need to find where is our initial configuration, our display. Oops. This is the second one. Okay, so we want to check the second genome value for each solution, right? And let's quickly try to find where we, in this case, we just have this guy, right? Okay. In which one we had the individual ones? I think here, right? Yeah. So if we open that guy up, and if we have our phenotype here, match the output. Okay. So of course we should also put our genomes here and our fitness values as well. I mean, we don't necessarily have to have our fitness values, but okay. So let's, I don't need this, but I need those. Okay, let's have it a bigger way. Okay, so we know that anything in this list, which is, okay, what we have in the second list is the initial configuration, right? So let's try to check manually if this value is has a kind of pattern. So if it's repeating itself. So we can see it's 1, 1, 1. Already I have a repetition. Okay. Okay, I still have 1. Okay, I have 2, 0, 3, 0, 4, 0. Okay, 5, 0. Okay, I have never seen 2, but I know that also 2 was an option, right? Yes. So, and which was the 3 different starting location. So I already have a feeling that this is not a good idea to go with it, because all the values that are closer to our fitness, to our fittest values have either 0 or 1. Okay, again, we are going back to 0. Okay. I mean, between 0 and 1, in order to decide which one is better, I think this list is not enough. I mean, I can see that 0 is repeating itself more than 1, but maybe if I run this algorithm with 5,000 iterations, then it will make a more dominated result. But there is one thing which is certain: we never have the initial configuration 2, which is quite interesting. I learned that right now as well. It's cool to know.
Yeah, I think I don't know if you have more time, but right now, for example, what I would do if this was my project and I had more time, I would maybe choose some of the worst ranking genomes that have 2 in it and figure out why 2 is giving such a bad result. It seemed like from the experiments we were doing earlier that with those 3 points in the middle, there's like a big gap. So maybe, you know, I don't know, it's really hard to say. I mean, you would have to go back and really study how everything is changing.
Also, yes, I agree with you. Maybe changing the overall distance between these 3 points can make a drastic change as well, because as you said, there is a gap in the middle. But when this gap is a bit less, maybe like, you know, a distance where we can only put 1 or 2 plots, then it might even give a better result because of the, you know, organic growth around these points. I don't know, maybe. Well, yeah, it's either way, it's interesting to learn that. And then, as you said, if if we had more time, it would be also nice to go back, change something and rerun, and then see if we really improved the design options that we are having or not. Yeah, so, but yeah, in this case, just running an algorithm takes 20 minutes and we only have 20. So I think for now, in this session, we're not gonna able to do that, but maybe as a final step, I can try to encourage people to try other typologies just for, fun practice. And let's close everything in the, let's disable everything in the, or even let's not try to do that, because we might want to have this in our final drive. Let's keep it as it is. But I also had a chance to try with the Voronoi, which I can also show it directly, and you can also see how it went, and we can also try to do something similar to that or different from that. Let me just find it. And in the meantime, if you have some questions, I mean, we are gonna finish in 5 or 10 minutes just to answer all the remaining questions. But since I'm looking for my file, also you can jump and ask. Let's also save this as a, let's say, DLA, organization, integration. Oops. Fine. Okay, let's put it and try to see what Voronoi gives us. So this was basically the same algorithm that I previously worked on it, but instead of, let's try to show, instead of starting with like a tile of pattern, I have Voronoi here, and for my boundary, I have a rectangle here, and for my points, I just have a random populate. But then again, for calling the list and making the pattern, I'm using the particles. And then I'm performing some kind of elimination process, extracting some of the areas and making some park areas. And then we have the same kind of variances here. And then let's try to just to have, maybe I already have some results here. Let's see. Okay, I have. Let's try to have the latest generation in order to have something on screen. So this is not a really a lot of optimization. As you can see, it's only 7th generation. All right, so export that.
Okay, this one looks much more computationally intensive, no?
Yes, also I wasn't expecting there is a 50 iteration in one generation. I didn't really remember that.
Oh, that's why. Okay, okay. Yeah, okay. That makes sense.
When I click it, I realized I made a mistake, but
Okay.
Yeah, in the meantime, we can really start for the Q&A session. And I didn't forget, I'm gonna add another variance before we finish it. It's gonna just take 2 minutes for Louis, because we just need to see how it looks like in the graph. So I didn't forget about it. But for other discussions, yeah, if you guys wanna share some thoughts and some question marks in your head, let's get started, and we can wait. No, it's fine. I also forget how it looks like, so I also would like to see the result. So
any comments on the general, on the workshop in general would also be useful for us, I think, because we also want to learn. I have some comments as well on the flow, but maybe to hear from you guys first.
exactly. I take that. All right, nice.
Thank you, guys.
And another question could be, if you guys have found what you're looking for example, I remember that some of you were saying you're going to study urban planning, or some of you already have some experience on it. So do you think those tools and the methods that we created today is going to help with your further studies and everything? So what do you think about it as well? Do you find it useful, interesting, or, you know? Maybe I can also make a comment for the first phase, which is for Rıdvan. I really didn't have a lot of ideas about the DLA part previously. I mean, we had a couple of sessions together, but I didn't really know the whole context and everything. And I think it was quite interesting to integrate it and deepen our reasoning to a DLA algorithm, because it has such a, you know, let's say studies and already going on research on it. So when we previously done our experiment in our phases and our you know, project you guys see, we were somehow in the beginning floating in the air when we are creating that urban organism, let's say. But also reasoning your pattern or tile or whatever, I think this also carried the work into another level. So it was nice for me to learn how we can create those algorithms and everything. So thank you for that part.
Yeah, and I can say the same thing. I mean, just having an algorithm is one thing, but then using it to make something meaningful, it obviously adds a lot to the work. I think, I mean, there's so many open questions here, right? So we have this workflow now, and it uses a growth algorithm that's different every time, but it's trying to optimize it as well. So there's a lot of questions like, how well can you optimize a process that's somewhat random, for example? It seems like we can do it, but there's still a level of randomness in it. And if you think about a real city, it's kind of similar, right? There's certain certain things that are constant that will always happen, but then there's also a certain level of randomness. So there's also a lot of theoretical questions and outcomes you can take from this process. Other than that, I also learned a lot just by watching the second part, because I had no idea about Wallacei. Actually, the one of the best things I learned, I think, was the tree. What was that? Tree mapper?
Yeah, path mapper.
No, not that one. Sorry,
Not
a
that.
data viewer.
Ah, okay.
It's kind of embarrassing. I've been using Grasshopper for like years now. I've never used data viewer before.
Well, I learned that 2 weeks ago at work, and I directly carried it here as well.
Very nice.
And I was pretending I know it for a long time. So yeah, I mean, there's a lot of things that we, work as a habit, and then we never check what is the other things. But I think it's quite useful. Yeah, it's much more visual and it's easier to understand. And about the other comments, I also pretty much agree. And one thing I forget to add is, right now we didn't really compare the numbers, but for example, when I was studying in sustainable architecture and using these kind of tools, it was a bit hard to convince people if it really does something, if you don't prove that with the numbers, right? Because, for example, we were using it for the facade study or something, and I was showing, okay, I tried this with 10,000 iteration, and this is the best result. And people were asking, how can we understand it? And when you compare, for example, in the first part, you have, when you first design, you put a number, and it's, let's say, it has a solar radiation value with a certain amount of number. And after that, when you have the final iteration, that this is the one that you selected, and when you show that you have, let's say, 25% better results with only small adjustments, it really makes a lot of sense, and it really convince people, right? Because in overall design, you're not changing much. You still have your idea, you still have your aesthetics and everything, but on the performance side, you have a lot of improvements. So when you're using it, definitely try to compare the numbers and show the actual growth and changes. This is a note, and this is from the Voronoi algorithm, which is quite fun. And I think I here forget to eliminate the big ones, so you can see a lot of giant. Oh, this is, for example, horrible. Yeah, but you can try to play with different kind of orientations and come up with something new. Okay, and I'm gonna also share that one as well. I messed the whole documentation a bit today, so I need some time, and then I'm gonna upload everything. Let's close that. And finally, also let's check if we put another objective, what's gonna happen before.
Can I just ask a question just before that, and
yeah,
maybe make a comment after that?
Sure.
I wanted to have your advices on two ideas I had. The first one is regarding the way that you are creating paths between the buildings. And I was wondering if it was possible to somehow reverse engineer the techniques that Ridvan showed us during the first session. The one from Bill Hillier, where he iteratively puts some blocks on the screen and decides whether to put an empty space or not, and repeating that step many times. I don't know if you remember. Maybe can I share my screens to show some?
Sure, go for it.
I don't know if I can do this.
In the end, we're gonna learn. Someone can share. Okay, nice.
No, it was something a bit like this.
Can
you see the screen?
Yes, we can.
Yep.
And I was thinking maybe we could use the same kind of techniques with the grids of squarish Voronoi cells that you built, and maybe take one cell, starting with one Voronoi cell or squarish Voronoi cell, one block, and look for the neighbors. Check if all the neighbors are touching this cell, and if all neighbors are touching, then we decide to remove one of them, and then go on like this, going through all the stack of cells, and at the end we should, I believe, end up with something like this with path. So it would be kind of the same logic showcased by Rivan and Bill Hillier, but instead of adding space, we would remove it based on the neighbors. If there are too much neighbors, we remove one. So I don't know if that makes sense. That would be an idea to explore for path making. That would be the first question, and maybe wait your response before asking the second one.
Okay. Do you want to go, Ridwan, or do I?
You can go.
Okay. First of all, I think, yeah, it's a very interesting idea to go with it. And I'm not quite sure how you can do that without diving into some coding.
Yeah, that would be with code.
Yes, because as I previously said, I don't have a lot of experience in coding. Therefore, when you say something, I'm trying to figure out it in my head within the limit of Grasshopper, but it could be a bit harder to do that in Grasshopper. So therefore, maybe Ridwan can, in the practical side, can give a better answer to that. But in the theoretical side, I found it quite interesting, and I think it somehow shouldn't be so hard to manage that kind of operation, right?
I'm not sure, to be honest.
Really?
Yeah, I mean, I don't think I'll be able to give much advice here, unfortunately. I mean, of course, the idea is really cool.
Well, I try to give it a try in the following days.
Yeah,
Maybe not before the deadline, but if I end up with something, I might send you, shoot you an email.
Yeah, that would be great.
And also putting a rule to this open spaces, something we are lacking right now because it's all based on randomness right now.
Yes.
Could really improve what we are creating, because right now it's kind of like an imaginary city with no rules. I mean, there are some base points that we're taking, some ideas, but we should definitely, in order to have a realistic case, we should definitely put those kind of small rules, right? So this is a good start to do that. Yeah. And if you find a way to do it, please, next year, let's join to yours.
Yeah. We'll attend.
I was thinking maybe adding some probability based on the area of the building. If it's a very large building, maybe we could remove more neighbors around it, stuff like that.
Mm-hmm.
The second question was about the growth algorithm. I was wondering if you had tested the genetic algorithm with other growth algorithm. One of the reasons I wanted to participate in this workshop, and I'm really glad I did because it was super interesting, is because I wanted to somehow combine the genetic approach with an algorithm I came up with a couple of years ago. Maybe I can show. It's also a growth algorithm, but it has some organic feel to it. And I don't know if you can see the things growing on the screen.
Super cool.
And I was thinking, so it's really simple, really simple rules. It's you have particles that are pushing each other, and when there is void, they are attracted by the void, and when there is too much density, they die. We remove the particles. And each time we run the simulation, it gives some, because there is some randomness in the parameters, it will give a different output. but I have to fine tune the algorithm and the parameters. But I was thinking maybe we could use, those particles, because if you look at it, it shows some common features with a human city. For example, when there is too much density near the center, particles die. So you have larger areas, and around you have denser areas, like like cities like Tokyo, I guess, where you have large buildings and large parks near the center, and you have residential areas around, right? And I was thinking maybe we could combine this type of algorithm with the genetic approach. But I don't know. Yeah, so I don't know what you think. Is it too far stretch? Is it too? I don't know. I'm not an architect, so it's.
I'm curious. How did you code this? Is it in or is it coded?
It is in processing.
Oh, it's processing. Okay. Okay.
There is a, if you're interested, there is a really nice.
No, the internet's.
Yeah, we can't hear you right now.
Can you hear me?
Oh, okay,
Yes.
right. Yes.
Okay, sorry. Just 1 minute.
Maybe.
Okay,
do the others have time? Maybe we can
I will
talk
stop
about
this
this
question.
afterwards.
Sorry about that.
No. I mean, I will stay. I mean, we can keep answering, but just to talk about everything that everyone needs to hear first, and then we can, because there's also the exhibition stuff. I think we want to make an announcement for that. Yeah.
So just as the last comment, I would like to say that I really enjoyed the workshop. It is really clear, obvious to me that you have done a lot of work beforehand to prepare stuff. I really enjoy the way you are helping each other, one suggesting to make a pose, reading questions, and proposing relevant comments. Really like this. As I told you before, it is one of the very few workshops where the pace was perfect, at least in my opinion. I really liked it, and I think you are making a great duo together. And also, I would like to say thank you for bearing the fact that most of us didn't show our faces. I personally don't like to show my face, but I know that it's really important for you to have some kind of visual feedback, to see if the students are interested or bored or surprised or anything. And yeah, by the way, shout out to Ege and Sarah, who opened the cameras and on behalf of us reacted. So yeah, thank you, and yeah, that would be all from me. Thank you very much.
Thank you very much for your contribution as well, with your interesting questions and your attitude. I think you also were a great part of the workshop as well.
Yeah, for sure.
So also thank you again. You also had a dedication, as Louis said, and we didn't feel alone during the whole session.
I need to leave now, but I'm putting my note here. So see you guys.
See you. All right, see you. Can we quickly talk about the exhibition stuff? So we said it a few times. So they're expecting some kind of outcome. It could be anything. They're not specific with it, and I think there's already some options to play around with within the files that we shared. So, for example, in the beginning, we said that really large blocks on the side, don't really work and stuff. But you could also, for example, make the large blocks have a height of 0 and consider it farmland, for example, and just make small towns or something. So you could just play around and come up with any kind of changes you want. use Voronoi, use other configurations, and see what you can come up with. Of course, our time is limited. I mean, we don't want to just, if you can just do something short, if you want to, if you're interested in it, and then send it to us, and then, yeah, we can exhibit it in the metaverse.
Yeah, and I'm not quite sure how it's gonna be presented, but maybe, I don't know, are we gonna join with our avatars or something?
I think so. I'd want to join. Yeah. It's going to be exhibited for like a month or so. So it's kind of going to be like a museum where you can go and you can just check it out.
Okay. Sounds cool. Yeah, just, there is not a lot of time, but just have fun. And if you want to create something, just as we already said, it really depends on your artistic preference and style and whatever. And it can be also like a emotional media, like, for example, Louis already showed something as differently, but that also bring an idea. Like, you don't have to create necessarily a JPEG or an image. You can create some kind of animation, video, GIF, anything as well. And also, thank you too, Noor. I just saw your comments, and thank you for all the other guys who have been here and dedicated the time, especially in the weekends, in the early times.
Do we have anything else? If we don't, then we can continue with the question from Louis.
Yeah, it would be nice. I'm gonna send the clip to Louis where I tested the fourth one because I don't want to go back to Wallacei interface. But
yeah, but it's fine. Really, it's fine. I really understood what you said, with the different coloring and stuff. So yeah, really, thank you.
Okay. So then we can continue with his question.
Yeah. So what was I saying? You coded in processing, and does it make sense to put it into genetic algorithm, or does it make sense as a city? Okay. So one of the things that helped us, I mean, the beginning part with the theoretical stuff that I presented, that information was what allowed us to make the reach from a DLA algorithm to the city, right? Because without reading other people who are talking about, wow, a city is a complex organism and it can be modeled in this way, it's really difficult to have that idea to jump from that scale to the city scale, right? So I think to have a strong base, you might want to look for those papers, like, for example, Reinhard Koenig's paper where he used DLA and was the cellular automata to make cities, was very helpful for us, because then we knew that we were doing something that could somewhat work. With your example specifically, I think it might be good to compare what you have with existing works who have used it for the city scale. If you're wondering if it would work for the city scale, if it's a big stretch or not. It's hard for me as well to say right now, looking at it, if it's a stretch. And you seem like you already know a lot of, I mean, you probably have an idea of the literature. So I don't even know if my opinion is more valid than yours, to be honest. But that's the only thing I would say. I mean, the first thing I always do is just go to Google Scholar and just search for a bunch of papers and see if I can find anything. And there's a few other simulations that came to my mind. There is the segregation model. Do you know the segregation model?
I do not.
Okay, it's a very simple model again, but it models how in societies people like to live with people who are similar to them, right? So it was used in the 60s in the US, for example, to figure out how how African Americans would kind of live in similar neighborhoods, and you know, the white Americans would be living in different neighborhoods, and why the segregation was happening, for example. And they made like a very simple agent-based or a rule-based model to model this. There was another one. I need to search this because I forget what it was. Okay, could you give me like 2 minutes? I need to search for something. I can't recall what it was.
And by the way, for everyone who has attended and we overpassed our time a bit, if you guys also would like to leave, feel free to leave, and you know, don't feel yourself obligated to stay. But if you are curious about further conversation, you're always very welcome to stay, of course. And thank you for Piyush as well for your comments also. It's glad that you also find it informative.
I'm not sure if I'm going to be able to find this.
Also, if any of you guys in the further stages that you are working something similar to the information that you have from this workshop, if you need any source reference or any kind of guidance, just feel free to send an email. Because it is also interesting for us to, you know, jump into something very different, and we might have some information we can guide you as well, and you can also guide us as well. So it's always nice to share the, you know, experience that we all have all together.
Add us on LinkedIn if you want. That's easier as well. Keep in touch.
Yeah. For example, we personally with Rudvan met on one of the Digital Futures workshop.
Yes, exactly. We actually met last year in a workshop. Yeah.
So you never know.
I can't find what I'm looking for. Unfortunately, it was a website with a lot of these models. You could just basically, there was like 30-40 models, and you could just click on it, and it had like a nice interface where you could play around with these models. And it's kind of annoying that I can't find it right now. Okay, wait. I think I got it.
I really don't want to waste your time. So if
no, this isn't waste.
Find it, okay.
I'm curious. Like I love this stuff as well. So
if you find it later, maybe you can send it.
Okay, no, I got it. I got it here. I'll send you this one. So this is Northwestern University's models library, right? So they basically have a whole bunch of, so they have ants, they have beehive, they have blood sugar regulation. The one I was looking for was Daisy World, actually, yes. Okay, I mean, there's so many, it's a really nice webpage, this one, because it has all kinds of models. And all of them are different. All of them have their own description. I can't explain it any better than they have. Here, they also have the segregation model. Yeah, I mean, take a look at these. See if you find something interesting. Yeah, that's probably
really, really nice. Amazing. Thank you very much.
You're welcome.
Yeah, I'm gonna steal that as well. It sounds super nice.
Yeah, I just remembered it now. I don't, it's been like 2 years. That's why I couldn't remember it, but I know that there's something like this exists. It's just a library of agent-based models and other this kind of local models.
I want to try each and every one of them right now. Thanks for sharing that. Yeah, it seems super nice.
Well, while we are sharing links, maybe you or the participants would be interested in the tutorials from an architect named Satoru Sugihara. I don't know if you've heard of him. He's actually giving a workshop right now on the digital feature platform.
Okay.
And he has created his own environment for particle-based design called IGO for processing, and he has a website. I will copy paste the link in the discussion, where he has tons of tutorials and actually learned pretty much everything about coding and about agent-based behavior thanks to those tutorials. It's both in Java and Python, which is really nice. You have nice pictures, and if you look on YouTube, you will find super cool outcome from his workshop sessions. So yeah, that's one thing. And the other thing maybe that could be relevant to the participants as well, but you mentioned it already, Ridvan, is the Coding Trains channel. There is a video on genetic algorithm, which is really, really nice, clearly explained, fun to watch. And it actually helped me a lot to understand today's workshop. Because I know that when we are facing with a screen with a lot of components and with new components such as Wallacei, it can be really hard to digest. But going through the basics of genetic algorithm could be a huge plus with those videos. That's all.
All right, thank you. Yeah, I'm looking forward to the link. Definitely, yeah. Sugihara, you said, I think, right? Yeah, after getting into the industry, like starting to work, I lost a little bit of like a touch with the academic side of things. Yeah. Okay. I think from my side, that's it. Thank you guys for participating. Thank you, Louis, again, for the discussions. I mean, it's really nice to be able to have these interesting discussions here. And participation is obviously really important for us. Yeah.
Exactly. And right now I see Darshan also send the link. Thank you for that as well. I see that there are a lot of educational resources, which seems quite nice. So we call it a day as well, and
I'm just gonna bookmark all of them, so if something goes wrong, I don't lose them.
yeah, I was doing the same. I saved the conversation, even though we have the records.
Yeah. Okay, so it's also from the same guy. Nice. Erwin. Okay, cool guys. Thank you. Thanks a lot.
We're gonna have the record again in the drive, if in case you want to rewatch it, and maybe in YouTube it's gonna publish. I'm not sure, but I guess. So like we speak, in case of any question and anything, you can just directly send an email. And for the submissions, if you want to create something, we have the drive. Just create your folder or change the folders that we already have, and feel free to do anything. And again, thank you for your contribution and your presence. It was a great 3 days of session, also from our side, and hope to see you guys again in some other time.
Yeah. See you all.
See you. Bye-bye.
Thank you.
Thank you very much.